Hey everybody, so today we're going to talk about some MPC ideas and we're going to go over homework 2 just for a quick run through. And then I'll show you an example of how we can do MPC on a nonlinear system like a quadrotor. And I'll work through the example, both the math, and then I'll show you the actual code that does everything. So let's get into it. Today is the 24th. Okay, and today we're going to look at the following. So MPC, homework 2, and then quadrotor MPC. Okay. So as a general background, this whole class is about setting up and solving control problems as optimization problems. So when we're doing that, what we're looking at is trajectory optimization. And what we're doing here is that we're doing min, you guys have seen this a bunch, minimizing over x from 1 to n, u from 1 to n minus 1. Then I'm going to have some cost function. And then we're going to have these dynamics constraints. These say that the x's and the u's that we're solving for must be dynamically feasible. And then we'll just also have some more, just a generic constraint. And this could be, anything we wanted to. So this is kind of like the canonical trajectory optimization problem. What we're doing is that we have this dynamical system that we can describe by these discrete time dynamics. We have some cost function we want to minimize, and we have some constraints. These can be path constraints, actuator constraints, a goal constraint, stuff like that. And the idea is that we want to set this up and solve this as an optimization problem. This is kind of like the whole theme of the class so far. And what we've done specifically in the last few weeks is we've looked at a few special cases of this where it becomes really easy to solve. So the first case we'll look at is finite horizon LQR. I know you're probably tired of seeing this by now, but we'll do it just one more time. Min x1n, u1, n minus 1. And then we have our stage costs, 1, n minus 1. Plus xn transpose qf xn. Have some initial condition that we constrain the first x to be. And then for the rest of the x's, they must satisfy the following dynamics. So basically what we're saying in this class is that we're going to start out with this general form where, we're trying to solve these control problems as optimization problems. And then what we're saying is that in a certain case, in a special case, what we can do here is that we can say that, okay, well, if they happen to look like this, if this is our problem, then we can be a little more clever in how we solve it. And what I mean by this problem is if we have this LQR cost function, which is quadratic and convex, Q is going to be positive semi-definite, R is going to be positive definite. I have some initial condition constraint, and my dynamic constraints are linear. So if my problem happens to look like this, I can solve it in two different ways. The first way we can solve this is solve with CDX. So this is a convex optimization problem, and that means that we can solve this thing very quickly. The theoretical bounds of these things, like we can solve these things in polynomial time for a global optimum. In reality, what you'll have to know is that you don't have to worry about where you start or anything. You can solve this problem for the globally optimal solution. And for problems that are the size of control problems, you can do so extremely quickly, like oftentimes less than a millisecond. So I can solve this problem guaranteed with a convex optimization solver. And this will give me my solution x's and u's. For x's, u's. Now, option 2, what we talked about in class, is that we can solve this instead with a Riccati recursion. So Riccati. And this gives us a different type of policy. And so it's definitely worth talking about kind of how these two differ and why we want one instead of the other. So the first thing we have is that we're going to have this kind of feed forward X and U. And what this is that I solve this convex optimization problem. I get a solution, and this solution is specific to our initial condition. So the solution to this problem is going to change based on where we are in the state space. And then what we'll do is that we'll take that X and U and we'll start at our initial condition, and we'll just begin just executing our U's. Now, the other option is that we can do a Riccati recursion, and this gives us a feedback policy. And when we do the Riccati recursion, we don't include anything about our initial condition. What we solve for is just a generic feedback policy with these gains K at every time step. And what we see is that it does not matter where we start in the state space, we will always act optimally if we do this. So this is a globally optimal solution, no matter where you are in the state space, assuming everything is linear. So now I'll kind of do a quick little drawing of what's going on here and why things don't always go the way that we'd like them to. So we're going to have a sim to real gap. Sim to real. And a lot of you have probably heard of this. And what we're talking about is, unmodeled dynamics. Noise, noisy actuators, things like friction and stiction, all these weird things that happen inside the actuators. State estimation. It's a whole bunch of reasons that we don't actually know what's going on with our system. So we have a pretty good model. We can do a pretty good job estimating how our robot moves, where our robot is, but all these things are going to have unknowns and uncertainties tacked on top of them. And this makes our control problem a little more challenging. And here's why. So imagine if I start, I have some, here's my initial condition. And over here, I have, some goal state that I'm trying to drive my system to. If I were to solve that convex optimization problem where I say that I must start at my initial condition, and then I go and I actually execute all those controls. So time step 1, I execute U1, time step 2, I execute U2, and I go and I do all these things. And if I read this out using my linear dynamics, it should look perfect, right? This is, the optimal trajectory. The issue is that when I actually go to implement this and I run this first control, for all these reasons right here, for all the sim to real gap causes, what I'm going to get is I'm not actually going to move the way I expect myself to. So what I'll do is I'll take this first step. I'm going to move just a little bit off where I thought I was going to. I take that second step and I'm a little bit off. The idea is that due to these things involved in the sim to real gap, due to these uncertainties in our system, I don't know everything about this world perfectly. When I execute all my controls, I'm going to end up moving differently than my model thought I was going to. So if I were just to run my controls in a feed forward fashion, so just run all the U's and just ignore any sort of input coming in, if I were to just run all my U's, I might get something like this. So this could be, U, CBX. Now that's a huge issue because basically it means that in order to actually get this thing to work, I have to resolve the problem at every time step, which is not the end of the world. This is a totally fine thing to do, but it's not something we have to do in the LQR case. So what we talked about is that we can solve this with convex optimization for a specific trajectory given a specific initial condition, and we can run this thing. And the alternative is that we can use LQR to get a feedback policy, which is globally optimal everywhere. And so what this means is that in this case, when I have linear dynamics with some uncertainty on them, I have two options. The first option is I can run my convex control policy, and I just run all the feed forward U's. And what we see here is that due to the things involved in the sim to real gap, I'm going to get some movement off of where I thought I was going to go. So I thought I was going to go up and down and hit the goal. And in reality, because the dynamics are a little bit different, or my initial condition was like a little inaccurate based on my state estimate, or there's noise in the system, I end up moving off this desired path and I end up missing the goal. And the idea is that the way to account for this is I can just, at every single time step, I can set up and solve a new convex optimization problem where I solve from a new initial condition. And this is totally fine. This is what MPC is. But why would we do this when we have our LQR feedback gains that we just said are globally optimal? So they work anywhere. And that means if I move off this manifold and I go up here, I can just execute my LQR policy and it's still optimal. So I don't have to resolve anything. I have my Ks, I have my optimal gain matrices at every time step. And as long as I execute those, no matter where I am in the state space, it will always just work out for us. So the idea is that feed forward is going to be in blue. This is UCVX. And if I just execute this thing blind and just run my U's and don't think about it, I'm going to end up missing where I thought I was going to go. Or I can just run this feedback policy, and no matter where I start, this is always UI equals negative KI XI. This feedback policy will just always take me to where I want to go because it is the globally optimal feedback policy solution. So no matter where I am in the state space, executing my LQR policy is going to be optimal. Or when I'm planning for this thing, I have to know the dynamics perfectly, which I don't. So that means that at every time step, I'm going to move off from where I thought I was going to be. There's going to be some error here. So I have some little E. I have an error here after every time step. And what I can do is I can just, okay, now I have a new initial condition and I have a problem that's one step shorter. Now I can just resolve an optimization problem. And you can do this, and this is totally fine, and we can solve this very quickly online. But it turns out that in this specific case, where we're dealing with a problem that looks just like this, so our finite horizon LQR problem, that it really just makes more sense to just use the Riccati recursion, get our optimal feedback gains, and execute that feedback policy. So that's kind of the story for finite horizon LQR, what we want to do when we run this thing. And so let me just go ahead and write some of those things down I just said. So if we execute UCVX, we will screw up a little. So if I just execute these U's from our convex optimization solution, I'm going to move off of the true optimal solution. I'm going to think I'm going to do X, but in reality, I'm doing X plus or minus some delta. And alternatively, if I use the Riccati solution, we are always optimal. So it does not matter where you put me in the state space, I can execute this control policy and I'm happy.
So, Kevin, I have a quick question.
Yeah.
This all makes a bunch of sense. I just want to quickly go over how we sort of arrived at the Riccati equations. Was it we essentially had the convex optimization and we sort of took it and like did introspection on the matrices and found that there were these reoccurring things and pulled stuff out. Is that correct?
So yeah, this is a really good question. So there's a few ways to get the Riccati recursion. So the first way that you were talking about that Zach went over in class was exactly this. What he did was he set up this optimization problem as an equality constrained QP, which you can do. And then he went through and he looked at the sparsity pattern inside these matrices and the structure in these matrices. And he saw that if you do some block substitutions on element by element wise, you can get this like recurring pattern that you recognize as a recursion. And you no longer have to just inspect everything. You can just, this recursion will hold for everything. So this is one way to do this. I don't love thinking about it this way. I think a better way is the alternative derivation he did, which is where you think about it in terms of like the value function and you do like a dynamic programming solution going backwards in time. So if you remember, I'll do a quick little like 2-second derivation of this. But if you remember that we talked about like the optimal cost to go function, and if I'm just going to assume it looks like this. So do you remember him for the LQR case? We assume that our optimal cost to go function is always going to be a quadratic. And what this means is that at the last time step, our optimal cost to go is going to be Vn xn equals xn transpose p xn, where this p, since we know our terminal cost is qf, this is qf. So what we do is that we initialize p of n equals qf. Now, the next thing we do is we say, okay, the action that I want to take, my optimal cost to go is going to be whatever minimizes the value function at the next state that I'm looking at. So we'll say that, okay, I have some model. This is xk plus 1 equals a xk plus b uk. I'm at xk minus 1, and I want to get to a point where v of k of x is minimized. So I want to like drive this thing down. So what we did is that we wrote this thing down as an optimization problem. We said that v of k minus 1 of x k minus 1 equals min over u of our state cost x k minus 1 transpose qx k minus 1 plus u transpose ru plus, and this value function at v k of ax k minus 1 bu k minus 1. So does this seem familiar to you? Do you remember him doing this?
Yep, yeah. Is this the dynamic programming formulation almost?
Exactly. So yeah,
And then
this is
yeah.
exactly the dynamic programming solution.
Okay, yeah, got it,
Yeah,
got it.
that's what it is.
Perfect.
And so
Thank you.
I think you understand what's going on. So I'm just gonna do a quick little like finish here. So what we're saying is that
Sure.
here's our stage cost, and here's our cost to go at the next time step. And we know that this thing is written down as a quadratic. So if I just plug in my quadratic here with p, and I just this whole function is just like it's all quadratic in x and u. So it means I just set this gradient equal to 0 and I solve for the minimum solution, and that's how I get my recursion. So I personally appreciate this derivation a little bit more. I think it makes a lot more sense. And you don't have to worry about like dealing with the sparsity patterns of the matrices. But the main point is that you'll see this Riccati equation written down from a few different derivations in a few different ways, but they're all numerically equivalent. So if you were to Google, like, my finite horizon LQR solution, you could find an article where the recursion looks a little bit different than what we have. And if you went and actually wrote up the code and compared it all, you see that it all ends up being the same. So just be generally aware that for the finite horizon LQR Riccati recursion, you will see multiple derivations and multiple different forms of this, and they're all numerically equivalent. Does that make sense?
Yeah, perfect. Thanks.
Sweet. Okay, so now we're going to shift gears a little bit. So what we just talked about how, for this specific type of optimization problem for the finite horizon LQR, that I can solve this thing using a convex optimization problem, or I can do my Riccati recursion and I can get my feedback policy. And now let's look at a slightly different case. So imagine that I had the following problem. Imagine I had min x 1n u 1n minus 1. And now for my cost, I have the following. I have, let's say, L2 norm, L2 norm of x minus x goal plus the L1 norm of u. This is my stage cost. And then my terminal cost, let's just say, we can do a quadratic for that. And then for my constraints, what I can say is I can say, I have my initial condition constraint. I have my dynamics constraints, and then I'll put some new constraints. So now I'll say that the norm of u must be less than or equal to u max. So that means that if u was a three-dimensional vector, this would mean that u has to be within some sphere or a norm ball, as you'll see it called. So u has to be within this set, which is a convex set. This is a convex constraint. Everything's fine. And then I can also say that let's put some bound constraints on x. So x must be between certain values. And then also let's just go ahead and put a goal constraint. And that means that at the last time step, x must be at our goal. So this new problem that I wrote down right here, it is a convex optimization problem. So I can solve this thing for a global optima whenever I want to, and I'll solve it very quickly. The issue is that this is no longer any sort of LQR form, right? This cost function is not a quadratic. There's no Q and R that satisfy our properties. We have norms, so this is convex, but this is not an LQR cost function. And then these are the LQR acceptable constraints. and everything down here, we can't put into LQR. So what we'll talk about in this class is that we'll reach a style of problem descriptions that no longer fit into our LQR framework. And a lot of problems do fit into our LQR framework, but a lot of these things, a lot of these constraints end up being super important to the performance of our system. And some of them we can't just like enforce online, something like we have to plan for explicitly. And so for things like these and costs like these, we have no choice but to solve this convex problem. So the first story I told in the first few minutes of this was, for this finite horizon LQR problem, I can I can resolve the convex problem at every time step when the initial condition changes from what I expect it to be, or I can use my LQR solution. And I said that, using the LQR feedback policy is just smarter because it's optimal everywhere and I don't have to resolve. Here I'm saying that I have no choice. I'm going to have to resolve every time my X deviates from what I thought it was going to be, which we know is always going to happen because there's a sim to real gap between the way that we think the world is going to work and the way the world actually performs once you go out there and execute this policy. So if you see stuff like this, don't get like scared. This is all totally solvable and you'll solve something like this in your homeworks. So the idea with MPC is that I just want to solve this control problem at every time step. And I want to execute that first policy, and then I just want to move on. So I know that seems like a little weird, but imagine if I have, this is like my desired trajectory. Right? Here's our X goal. And here's XI. So what I'll do is at this first time step, I'm going to solve the convex problem. It's going to give me a U. It's going to give me an X, all my X's and all my U's. I'm going to execute U1. And what that'll do is I'll perform that action, and that'll put me here. And what's going to happen is that there's going to be a little bit of an error between what I thought was going to happen and what actually happened. And this is because there's unmodeled dynamics. This is our sim to real gap acting. So the issue is that once we move off of our optimal trajectory, we now have to resolve this problem. Because we thought we had X1, X2, X3, U1, U2, U3, and we constrain these things to satisfy our linear dynamics. And then we go and we run U1 on the robot, and we see that the X2 that we observe is not the X2 that we thought we were going to get because there's those slight discrepancies. So what we have to do is we have to now set up and solve this problem again. So now we have our error right here, and what we do, we just solve this problem again. This gives us a new action, goes here. And again, I look at this and I see, okay, I now have an error again between where I thought I was going to be, where I actually am. So the idea with MPC is that at every single time step, I'm just going to resolve this optimization problem. I'm going to execute the first control command of this. And it's always a little weird thinking about this because what we're doing here is that we're at every time step, we're checking in a state estimate, making it our initial condition. So here we go. I'll label this. This would be MPC input. So at every time step, I get a state estimate from either my state estimator or my sensors or whatever. And I take this estimate of what I think my state is, and I plug it in as my initial condition. And then I solve this optimization problem. And I take my first U, the first control in that sequence, I execute that control, and then I move to the next step, and then I get a new initial condition, and now I resolve this same optimization problem, and I get my X's and U's. So this is the general idea with predictive planning, if you will. And what we're doing here is that we're trying to use our model, which we think is approximate, but is pretty good. We want to use this for planning into some horizon into the future, planning at every single time step, and getting a new command. And I think that there's a little bit of confusion surrounding this with respect to how it actually deals with noise and uncertainty and any sort of like adversarial anything in our environment. So this will certainly drift from the real solution because of our sim to real gap. The question is, if I had a feedback policy, I could stabilize about this solution and everything would be fine. And there's no inherent feedback part of MPC. There's no explicit feedback term saying U equals, some gain times delta X. Instead, what we have is that we get effectively we get feedback performance because we are piping in the MPC input. We're piping in this new state estimate as our new initial condition. And what we see, and you should definitely go and try this, is that if I add noise to the system, I try and operate like this, MPC will account for all this noise and it will give us feedback performance without any explicit feedback term. And so I guess like a good takeaway from MPC is that if I do predictive planning fast enough, and I replan this problem with at like enough of a frequency, what I'll see is that I get this feedback performance without having to bake in any sort of explicit feedback term. So the next thing we should talk about is like our MPC horizon. MPC.
Hi, Kevin.
Yeah.
Yeah, one question. For example, here in the MPC example, I can see that the trajectory is not as smooth. Is it a way to guarantee the smooth trajectories from an MPC controller?
So is there a way to guarantee the MPC controller is smooth? So I guess what you're talking about is that, the solution to this problem may be smooth, it may not be smooth. So I guess in general, there's no guarantee of any of this to be smooth, right? So what I put here is I have an L1 cost on my control. And what an L1 cost will do is it'll encourage sparsity in U. So that means that it will, if I look at U over time, it'll have as few entries in U as possible. So what's going to end up happening is that I'm going to have like a big spike in U here, big spike in U there. It's going to have, let me draw this out. Optimal U is going to look like this. It's going to be like, 0, 0, 0, and it'll be like a big spike, 0, 0, 0, big spike. So in general, there's nothing wrong with having a solution that's non-smooth. In fact, it's if you put in something like an L1 cost or an L2 cost, it's likely that our solution will not be smooth. Now, what you're talking about is if I look down here at this little diagram I did here, where I said that, here's our optimal trajectory, but we see is that we end up moving a little bit off it each time. So you get like a little bit of like this feedback effect where there's some errors and I'm compensating for the errors. There are things you can do in this problem to say that I don't want my U's to change that much. And that is like a design choice on your end. So if you didn't want U to do this, if you like don't want this behavior, then certainly don't put in the L1 cost, right? A quadratic cost is nice because everything ends up being smooth. But if you had a system where U was like our fuel usage, so say you're on a spacecraft, so you do this in your homework. If I have a spacecraft and I have thrusters and my U is me firing my thrusters, I want to fire those things as little as possible. I want to conserve my fuel. And the fuel of my spacecraft is going to be the L1 norm of all those thrusts over time. So the sum of the absolute values of all those thrusts. So there are some cases where we're okay with a non-smooth system or a non-smooth solution, and we can encourage this behavior with our cost function. Now, if you had a system where you really want smooth behavior, you could use a quadratic cost. You could use your LQR cost, and you would never get something that looks like this. You'd always get like a nice smooth U. So if that's important to you, that's something that you can bake into your cost function or your constraints. What you can also do is that you can say, I have some nominal plan, a U bar. This is the U that I want to execute. And I can constrain my U to not be too different from the previous U. So what I could do is I could add this constraint that says, so here's like U old. And I could constrain that the absolute value of U minus U old must be greater than some delta U max. So if I didn't want my U to change that much between time steps, I could just explicitly encode this as a constraint in my optimization problem. So in my MPC problem, I could say, okay, solve this new problem. Keep in mind that this first control, this U1, it must only be a certain amount away from my old U. And this is like super common. This is a slew rate constraint is what you'll see sometimes. But basically, like I don't want my U's going over like crazy. So what's very common in robotics is that we drive torques to these motors. And it turns out that in reality, if I try and command two wildly different torques at different time steps, it's very hard on it's hard on the battery, it's hard on the actuators, and you'll end up getting like kind of weird performance if you do so. So it's just super common that you put some constraint in there that says, don't radically change U too much. And this is kind of like the great thing about MPC is that all these, basically you can be super picky. I can have all these very specific things that I want my system to abide by, and I can just encode them all as constraints, and I can use my cost function to encourage or discourage whatever behavior I want to. And none of these things fit into LQR, but this is fine because we moved out of the territory of LQR, and now we're like, okay, we're going to solve a convex problem at every time step, no matter what. So we might as well be as descriptive as possible and put in all those constraints that we care about. Does that answer your question?
Yeah, thank you, Kevin.
I have a quick follow-on question. This blue line that you've drawn, while it looks very sort of discontinuous, it's still dynamically feasible, right? Because what the problem we're solving requires that these trajectories to be dynamically feasible from one time step to the other. So if this was a car, this wouldn't look quite this like discontinuous. It'd look a lot smoother, right?
Yeah, so imagine I have this is my model that I'm planning with. I'm planning with a linear model, but in reality, what I have is I have this. So this is a linear model that I'm planning with. This is my like, in this case, it's approximate. I don't know my full dynamics, but I have a linear model that I think is pretty good. And then I have some true dynamics. So what we're saying here is that this initial trajectory that we planned from that first starting point, the black trajectory, is dynamically feasible according to this. So that first one that we planned, this black one, it's like, hey, like this works perfectly. I found the optimal solution. And then I go and execute it and I realize that I'm actually moving according to these dynamics, not my nice linear model. And what I see is that I move a little bit off at every time step. So the blue trajectory, I'll write this out. So the blue trajectory follows this solution. Sorry, the blue trajectory is dynamically feasible according to the true dynamics. And the black trajectory is what I thought was going to be feasible according to my linear dynamics. Does that make sense?
Yeah, perfect. Thanks.
Okay, awesome. So now we can talk a little bit about our MPC horizon. So what I wrote up earlier was I have this problem and I'm solving from 1 to n. And if I'm looking at like a finite trajectory, like I want to get from point A to point B, I'm driving to some goal, like in a finite horizon fashion. What I said before was that, okay, I can just resolve this problem. So at time step 1, I solve from 1 to n. Time step 2, I solve from 2 to n, 3 to n, 4 to n. So this horizon of my problem is getting shorter and shorter every time. Now this is totally fine. You can do this. What's a lot more common is to instead just choose a specific window or horizon size. So what I can have an MPC controller and I'm gonna say, all right, look, post just from now until the end of my trajectory, look just 10 or 20 steps forward. So what's a lot more common is that we'll have an MPC horizon. So here's some terms: horizon, window. And what this is saying is that at every time step, if I look at, here's our time, here's our current time, the window is going to look at the next n time steps. So instead of forming this whole problem where I optimize over the whole trajectory, to make things faster and easier, I will instead just optimize over the next 10 time steps, 20 time steps, like 100 time steps. And I can choose this horizon. This is going to be a problem specific thing. This will be dependent on how long it takes to solve this problem, how much foresight your controller is going to need. This is kind of like an engineering decision. But normally what's very common is 20 time steps is like a pretty standard horizon people will use, like something in that ballpark. So instead of optimizing from now until the end of my trajectory, what I'll do in MPC is I'll say, okay, I'm gonna optimize over some window of 20 time steps or something. And what this lets me do is that at every single time step, my controller gets a new initial condition. It's gonna think about or optimize over this horizon of n MPC time steps. And then from that, it'll return a new solution. I'll execute that first command U1, and then I'll take a step with the real dynamics. Does this idea of like having like a horizon make sense and why it might be advantageous to use both the same horizon, but also have this be, smaller than the full problem? Okay, so now let's see, what can we talk about? So I think this covers in general the idea of MPC. So I personally think that MPC is kind of the most important takeaway from this class. And I am pretty sure that most people in their project are going to use something like MPC. So what I'm going to do now is that we have a homework that just went out yesterday or 2 days ago that has a bunch of MPC type stuff on there. And then for the next few recitations, what I'll be doing is I'll be going over like example MPC problems. Because I feel that you kind of have to see this in code a few times to kind of understand like what's going on, and then try it yourself to make sure things work the way you expect it to. So for the rest of this, we have like 20 or so minutes left. I'm going to do a run through of homework 2 and kind of like talk through each problem and like what we were thinking when we wrote these problems. And then at the very end, like maybe the last 10 minutes, I'll do a run through of how to use convex MPC on a nonlinear system for a quadrotor, which is a super common thing in robotics. And hopefully like just seeing more and more examples of MPC will get you thinking, in the MPC style way. And then hopefully this will show up in your projects. So with that being said, stop this. And then let me go here. And then let me open up. Okay, sweet. So now I'll share screen. So can you all see the screen all right?
Yep.
Okay. So now let's go over the homework real quick. So question one had some quick Julia warnings. Basically, there's a few things that we saw people do on the last homework that are not so great practice, and we thought we could make things like a lot quicker if we just like give some general disclaimers. So the first one is that people were doing functions inside of functions, which generally is okay, but it can be weird if you need to diff stuff like this. And basically what happens is the compilation time takes forever. So don't do this unless you feel like there's no other way. And if you feel that, then come talk to us because I think we can figure something out. The second thing is that if you're using forward diff to diff through a function that has one input, you don't have to do this closure as the first argument. This is what we do when we have a function of multiple inputs and we want to take the derivative with respect to one of them. We can do this. If I have a function that just has one input, there's only one thing I could take the derivative with respect to. All I have to do is just do Jacobian, naming the function x. And again, this, for whatever reason, this adds a bunch of pre-compilation time, which can slow down your program. Okay, so question one, we're looking at the double integrator, which is what Zach's gone over a bunch. So imagine like a 2D plane, and I have like a puck on ice just skidding, and my control input is the acceleration I apply to it. So here's our continuous time dynamics. And what you'll do is you're going to discretize this model using the matrix exponential. So if you haven't done this, go watch the first recitation where I went over this. And then we're going to talk about this finite horizon LQR problem, the one that I just wrote up. We have our initial condition constraint, we have our linear dynamics constraints. And what we'll do is that we're going to set up and solve this problem using convex.jl, which is a convex modeling package that I showed in the last recitation. There's a whole video on that, as well as a notebook where I kind of just have all the general examples. And so what we'll do is that we're going to set up and solve this problem inside this function called convex trajopt. We're going to take in A and B for our system, our cost matrices QR, QF, the horizon size, and our initial condition, and we're going to spit out the optimal X and U. So we're going to show that this is in fact a convex optimization problem. We can solve this, we can get our solution. And the next thing is we're going to look at Bellman's principle of optimality. So Zach mentioned this, and he was like, this is so simple, it's crazy. I feel that it takes like 2 or 3 times of seeing this for it to really click because it's kind of deceptively simple. But the main idea is that any sub-trajectory within your optimal trajectory must also be optimal. So a way this was once explained to me that I like is imagine if I was flying from like San Francisco to New York City, and I was flying from SFO to Austin to New York City. If there was a more optimal way to go from either of those 2 legs, I would have taken it. So if I have an optimal trajectory of me going from a start goal to an end goal, any point within there, it is also the optimal way to get from the beginning end of that little section. And so what we'll do is that for this problem, we'll show that if I take my optimal trajectory and I stop it halfway through and I resolve this problem with my new initial condition and the horizon being shortened, I get the exact same trajectory. And this idea is critical for all this stuff when we do like the dynamic programming solution, is that we're acting under this assumption that every sub trajectory within our optimal trajectory is also optimal. And then we'll talk about finite horizon LQR via Riccati. We will do the Riccati recursion and we'll get our Ks. And what we'll see is that this ends up being the exact same, like, down to whatever our like accuracy is in our computer. This will be the exact same solution as solving the convex problem. And then we'll kind of talk a little bit about why LQR is so great. So the first one is that I don't have to resolve this problem when I change my initial condition. And the second is that I can now drive my system to any goal state. So I don't have to specify what my goal is when I form and set up this problem. I can just use the Riccati recursion, get a bunch of Ks, and I can use those Ks to drive my system to whatever goal I want to. So this is the general gist of one. And the last thing is we'll do like infinite horizon LQR. And this is just, you're just going to plot out and see that when you do this recursion, or a lot of time steps, that your values of both P and K end up converging. So what it says is that if I'm doing a finite horizon LQR where I'm looking at, 100 time steps versus 1,000 time steps, there's a certain window where if I go far enough, that first control input doesn't really change, right? If I'm thinking about 10 years in the future or 11 years in the future, that first control input is probably gonna be the same. So the idea is that we have this infinite horizon LQR gain, where if I do the finite horizon Riccati recursion, I do it for long enough, I'm going to see that my cost to go, P, and my control gain K are going to converge on steady state values. And this is what we call our infinite horizon LQR. So problem 2, what we're going to do is that we're going to do LQR in a nonlinear system. And we're going to kind of do it in 2 different flavors. So first thing we'll do is this little linearization warm-up. I'm just writing out what our Taylor series is for these dynamics. And I know that you'll probably see in class, Zach is always using these deltas. So I think it's worth explicitly defining what these deltas are and how we write down our linearized dynamics. I know for me, I have a little trouble when someone just says like, oh, we can just linearize it and solve it. I need to be like a little more specific. What are we linearizing? Where are we linearizing it about? And what is our new like coordinate system with the deltas? The idea is that we can write down this Taylor series in 2 different ways. So if I have deltas defined as they are right here, I can define my Taylor series as this with no deltas, or I can substitute in just a straight substitution, and I can get the following, which is a exactly equivalent thing, but now everything's in terms of deltas. So this is like what you'll see Zach do. And what we'll do is we'll do the cart pull, where we have this thing where it's like a cart and a dangling pole. The idea is that we're going to have some trajectory that's going to swing this thing up, and the model of the system that we use to plan is going to be different than the model of the system that we're going to use in simulation. And what we see is that if we take this swing up trajectory that I've made for you, and you try and execute this on the real parameters, it won't actually swing up all the way and it won't work. So what you'll do is you'll use a time varying LQR controller, and you're going to stabilize this system about the trajectory, which I think is a fun thing. And you'll also do a infinite horizon LQR about an equilibrium. So imagine if I have cart pull with the inverted pendulum on top of it, and I want to drive this thing down to like the 0-0 position where the pole is straight up and down and the cart is right above the origin. What we'll do is we'll use an infinite horizon LQR gain linearized about this point, and then we'll start at some off nominal point where in general it would fall down, but then we add our controller and we'll see that this thing will stay up. So this problem should give you a pretty good sense of how we apply these linear optimal control ideas from LQR, and how we can apply them to nonlinear systems. Then question 3 should be super fun. Question 3 is we're going to do sorry, it looks like we got a hand raised by Juan.
Yes, Kevin, one question. For example, in the previous exercise, can we use for solving for the infinity gain control systems package, or do we have to do the recursion for infinity?
Yeah, you have to use the recursion.
Okay.
So you will have already done this in problem 1. You've done the recursion in a few different ways and the infinite horizon one. So you'll write all these functions and you'll use all of your own stuff. So yeah, I should probably make that explicit, but you should not use any sort of external control package to solve any of these things. The idea is that we're like walking you through step by step so you can build your own package.
Okay, thank you.
So question 3 is going to get at a little bit of what I've been talking about today, which is, is LQR the answer for everything? And it turns out that it's for a lot of problems, it's not the answer. And what we'll talk about how to rendezvous a spacecraft with the International Space Station. This is true for any 2 objects in orbit they're trying to rendezvous, where one of them has a circular orbit, which is what the ISS has. And so it turns out there's this famous result that came out like in the 50s, where it turns out that the relative orbital dynamics of 2 spacecraft, where one's in a circular orbit, it ends up being pretty much a linear system. And this thing is so accurate, like this is what they use to do all the rendezvous with the ISS. So we're going to use this model. This is like a true model that everyone uses. And because this is linear, we're going to discretize this using our matrix exponential. So the same thing we did in the first problem and the same thing that we described in the first recitation. And then we're going to try to use LQR on this, and we're going to see what happens. And what happens is that when I use LQR, I try to rendezvous these 2 spacecraft, they kind of like hit each other a little bit. And so like, the smaller spacecraft kind of comes and like goes like within the bigger one before equalizing about a certain point. And this is a great example of how we can't encode state constraints into our LQR problem. I can't tell this thing, drop it down to 0, but don't go below 0. So what we do is that we then turn to convex optimization. We say that, okay, now I can specify all these things. So now I can say that, this constraint right here tells me that I can't go through the spacecraft. I must stop right at it. And then I can have a goal constraint, which says that this final position must be right at the goal. So what I've done here is I've taken the LQR problem, and I've now kind of baked in a few of these things that you can't capture in an LQR solution. And then we'll go and we'll execute this. We'll see how the rendezvous works perfectly. And then the last thing we'll do is it will extend this to MPC. What we'll say is that imagine I have some large amount of model uncertainty, and say every step that I go and execute turns out that I can't actually capture all this behavior. So what I'll do is instead is that I'll take a step, turns out I move a little bit off, I have some error, and then I'm going to set up the convex MPC problem, solve it again over some horizon, and keep doing this. And so this problem kind of like walks you through how to set up your first MPC controller and how to run this on what I think is a pretty cool system. So that is homework 2, and you have quite some time. That's due like March 15th. So it's the Wednesday after your spring break. So you have a bunch of time for that. Now, in the last few minutes, I'll go over yeah. So now I'm going to go over relatively quickly just an example of doing MPC on a quadrotor. So what we'll do, the first thing is that I have this model right here. So we shouldn't worry too much about this model right now because Zach will be going into this in the next few lectures. But I have a quadrotor where this is my state. I have a position R, a velocity V, and then this P is a modified Rodriguez parameter, which don't worry about that right now, but basically it's a way to encode my orientation. So instead of keeping track of a quaternion or a rotation matrix, this is just one of the alternatives. And then I have the angular velocity. So don't worry too much about how this works, but just know that I have a quadrotor and I had the dynamics of the quadrotor written down with this state parameterization. And if you've done quadrotor stuff, this is relatively standard. You'll see that, I can only provide lift in one direction. Here's the total force in the body frame. Here's the rotor torque in the body frame. And then here's the ODE of everything. I'm then going to use RK4 so I can discretize this. And again, if this is like not interesting to you, like feel free to ignore this. But in general, this is how we take a continuous time quadrotor model and how we discretize it with RK4. So this is our model, the system we're looking at. And again, everything here is in 3D. So I know Zach has done some planar quadrotor stuff. So this is the not planar. This is the 3D version of it. Okay, so we just assume we have this, we're just given this model F, right? This is, our discrete time model F. And then this is the exact same thing that I put in question 2 of the homework. And so again, we'll see that we have 2 different ways to write down this Taylor series. So when I say linearize my dynamics, I'm talking about one of these 2 things. I can either write down the Taylor series like this in terms of X and X bars, or I can write down in terms of deltas. And so one important thing to note here is that I have these bars, so X bar, U bar. And the idea is that I want to linearize about some reference trajectory, X bar, U bar. And this is my linearization point. This means that when I define my deltas are really X is X bar plus delta X. And so what I'll do for this problem is that I'm going to use this linearized model in 2 different ways. So I'm going to solve an MPC problem for the nonlinear quadrotor using the linearized approximation from this one, so no deltas, and then solve the same problem with deltas, and I'll show you that these things are equivalent. They are numerically equivalent. And so here's our MPC problem. So here are the 2 problems I just described. So the first one is I'm minimizing over X's and U's. I'm trying to track some reference trajectory. So this is actually pretty important. So the terms that you'll see Zach use is reference trajectory, and it kind of means 2 things. It can be a trajectory that you're trying to track, or it can be the trajectory that you're linearizing about. And oftentimes these are 2 in the same. So what I've done here is I've written out this thing in full generality. So there's no assumption here. These are the same things. So I linearized about X bar, U bar, but I'm tracking X ref, U ref. And there's lots of times where these will end up being the same. But I guess I wanted to make the point that these don't have to be the same. These can be different. And we can write down this problem in the same way. And in no loss of generality, we can have the capability to do whatever we want to. We can move these things separately. So the first problem is we're minimizing over X's and U's. And so here's our cost function. We're just doing an LQR tracking cost on X ref, U ref. I have my initial condition, And then I have this linearized dynamics model that uses XU and X bar, U bar. This is the first of the two Taylor series that I wrote down. And then I have some control constraints where U must be between U min, U max. Now, equivalently, I can write this thing down in terms of all the deltas. So now I can minimize over delta X, delta U. And if I just take my X equals X bar plus delta X and U equals U bar plus delta U, if I take those substitutions and just plug them into the first problem, I get this problem right here. And the idea is that sometimes you'll see it written down like this. Sometimes you'll see it written down in the first way. These are both totally fine and they're both equivalent, and you should feel free to use whichever one you want to. Zach will almost always use the second one, and he will always use the deltas. So when you see him using this is the same as this. So you shouldn't let that like at all confuse you. So the first function here, this is get Jacobians. And what this will do is that this is just going to take our discretized model using RK4, and I'm going to compute the Jacobians A and B. So this is the derivative of xk plus 1 with respect to xk and uk. I'm going to store all these matrices inside A and B, and these are going to be vectors of matrices. And then this function here, this is my convex MPC controller full. So I have full and I have delta. So the full one is going to set up and solve this problem. The delta one is going to set up and solve this problem. So the way this works is that I'm going to get the slice of the current trajectories that I care about. So X bar, U bar, X ref, U ref. And what I'm doing is that I'm thinking about this window. So I have a window, which is the horizon length for my MPC problem. It's thinking about this far in the future. This is n MPC time steps. And so I'm going to grab my reference X bar, or sorry, my linearization X bar and U bar from that window. And I'll take my reference X ref, U ref from that window. And then I'm going to create these variables in this package. And what this is that it's going to be a 2D matrix where I have the number of rows is the number of states and the number of columns is the size of the horizon. And same for the controls, except it's NMPC minus 1. And then my cost function, this is how I write down that LQR tracking cost, minimizing between X and X ref, U and U ref. I then have some initial condition. So I say that like this first X must be equal to the X initial condition that I got as the input to the function. And then I go and I get my Jacobians. So I'm going to linearize my system about X bar, U bar at every time step. You don't have to do this. So this could be done once offline. If you won't change X bar, U bar, this will be done once, and then you'll just feed this to your controller. But just to show everything in the same place, I'm doing it every time step. And this is where I add, you'll recognize this is my Taylor series. So X equals F of X bar, U bar plus A times, this is our delta X plus B times delta U. So this is me writing down the first of those two Taylor series exactly. And I just add this as my constraint to my problem, optimize over it, grab my optimal U value, and I just return that first control input U. So I can do all the same stuff in terms of deltas, and this function is going to be identically the same. And what this does is that this takes all the same stuff, everything here is the same, but now I'm creating delta X, delta U. And now if I just substitute everything in, so remember X equals X bar plus delta X, I can write down my cost function like this. And then now my initial condition constraint looks like this. And then here are my dynamics constraints. So here you recognize that I'm using the delta version of this. And then again, I just solve for that first value of delta U, and I return U1, which is U bar 1 plus delta U1. So here's our actual problem in sim setup. So we have number of states, controls. This is the length of the whole sim, some DT. Here's our initial condition. And then we're going to linearize this system. So our X bar, U bar that we're linearizing about, this is just going to be about hover. I'm going to take the quadrotor, assume it's just sitting there hovering, and this is these are the rotor controls that are required to make this thing hover perfectly. I'm going to linearize about this point. Then I set up my cost matrices, Q and R, to be this. Here are the model parameters for our system. So we have mass, inertia matrix, gravity, L, KFK, and these are like our two constants for the motor. And then I have this X ref, U ref. And so what X ref is I just drew out a infinity symbol, and I'm just going to try and track this thing. So this is my tracking trajectory. I'm tracking just like in infinity loop. Then I say that my MPC horizon is going to be 40. I have some X min, U min. So you'll see, I can actually put these in the problem. You can if you want to. And then my main sim, what I'm doing at every single time step. So X sim, U sim, this is where I store my simulation data. So at every time step, I update U sim I to be convex MPC controller, and that can be either full or deltas. We just wrote both those functions. And then all we do is that we just feed it our initial condition, which is our current state, xmi, and the current index I. And then we do is that we execute this control command, usim, and we just keep doing this. So I'll solve this again. And then also there's a package called progress bar where it lets you add these things to for loops, which could be cool. But here we can see that if I just take a linearized model of the quadrotor about a steady state hover, I can have it track some pretty interesting trajectories. So here's, I'm not sure why you'd need the quadrotor to do this, but we can basically do whatever we want to. So hopefully this is like a pretty good demo as to kind of how these tools work, how you actually write one of these controllers, how this would work kind of in the loop with the sim. So I'll make all this code available to you guys afterwards. And then what I'll do for the next few recitations is I'll keep doing examples like these. So I'll like think of a system, talk about how we can linearize this and tackle this for convex MPC, and then demonstrate that we can actually do this thing. The whole thing where I showed you the difference between doing things in full X versus delta X, I will probably just do that for this one. But if you have questions on how that works and why that works, always feel free to ask on Piazza or email me or anything. So this, I think, is a good place to stop. If you guys have systems that you think are cool and would like to see like case studies on in the next few recitations, feel free to like email me or write on Piazza. I have a few planned, but if there's specific systems that are of interest to you guys, I'd love to know them, and we can just do them in these problems, and you can see like how a system that you care about actually gets controlled with an MPC controller. All right, any questions for anybody?
I have a slightly different question. So, we assume here the states like that we get are accurate, like real, right? Like accurate, like there is no error for state estimation. So when there is some error, like there are sensor errors, how do we incorporate that part?
Great. So you're going to do this in question 3 of your homework. So here's the loop for question 3 of your homework. The first thing we do is that we'll get some state estimate so that this will have some noise. This will not be exact. The next thing we'll do is that we'll get, we'll choose what our reference trajectory is for this window. So from the current time step to n MPC time steps in front of me. And then we're going to call our MPC controller. And then what we'll do is that we're going to plug in our U into some thruster model, which will add some errors to it. So the idea is that there's a huge sim to real gap. This is caused by both uncertainty in our dynamics, but also it's caused by our inaccuracy in our state estimate. So we don't really know where we are, right? We have a general estimate of where you are. And all these tools will still work in the presence of all these uncertainties. The stability of them is questionable, and there's really no guarantees on these things. But for the most part, in most like robotics applications, if I have a decent state estimate and a decent model, I can run MPC and I can get some pretty cool results. So what you'll do in question 3 is that you'll kind of go through like how to do all of this when you don't know the two things that you just mentioned. I don't know the state estimate and I have like some model uncertainty. Does that answer your question?
Yeah, but in a lot of cases, like we have a separate controller, we have a separate observer. In this case, is it together, like merged together, like for MPC?
No, so this like state estimation function is totally separate from our controller, right?
Okay, I think. Oh, I see. So state estimation function is coming from the observer. You're saying.
Yeah, exactly. Yeah, this state
Okay.
estimate is our observer. So I just assume I have some block here. This will take in sensor measurements from our observer. It'll run it through a Kalman filter or something, and it will give me a state estimate, and it will update this in time. So you can treat these things as entirely separately. There is some like cool research where you can kind of do some belief space planning where you kind of incorporate these things together. But everything that we'll do in this class, we're going to keep them totally separate. So we just have a chunk over here is going to do state estimation, and then chunk up here that does control. And all we need from one to the other is just the controller has to tell the state estimate what the control was, and the state estimate just has to give the controller what the current state is. So that's the only connection between those two.
Okay. Got it. Thank you.
All right, cool. In that case, have a good weekend, everybody. I will see you guys next Thursday, I think, because Zach's out of town. All right. See y'all.
Thank you.